This is a sound, not a single note, a chord. Two pure tones played at once collapsed into one messy wiggle of air pressure. And here is a question that sounds impossible. Given only this one tangled line and nothing else, could you pull the original notes back out? Could you unmix the sound? The answer is yes, and the idea that lets you do it is one of the most beautiful in all of mathematics. Start simple. Every sound you have ever heard is just air pressure rising and falling. A speaker cone pushes forward pressure up. It pulls back pressure down. Track that pressure over time and you get a wave. For a single pure note, the wave is a sine, smooth, regular, repeating. The note we call a concert pitch wobbles the air exactly 440 times every second. That number, cycles per second, is the frequency. It is the entire identity of the note. Higher notes wiggle faster, lower notes wiggle slower. A 440 packs 440 cycles into a second. The D below it, 294. Middle C, about 262. Each pure tone is one clean frequency, one sine wave. Simple. The trouble starts the instant you play more than one at a time. When two notes sound together, their waves do not take turns, they add. At any instant, the air can only be in one place, so the two pressures sum into a single, more complicated curve. And that curve does not wear its ingredients on its sleeve. Look at it. Nothing obviously says 2 hertz or 3 hertz. The recipe is in there, but it is scrambled. So how do we unscramble it? Here is the trick, and it is genuinely clever. Take the graph of the signal and wrap it around a circle. Picture the flat waveform as a strip of tape, and you are winding that tape around a central point. How fast you wind is a dial you control, call it the winding frequency. As you turn the dial, the wrapped-up signal traces out these strange looping shapes, and hidden in the symmetry of those shapes is the answer to everything. Watch what the dial does. At most winding speeds, the shape is a tangled mess. The peaks of the signal land scattered all around the circle, unbalanced. But turn the dial to exactly match the signal's own frequency, and something clicks. Every peak lines up on the same side. The scribble collapses into a clean loop, heavy on one edge. That lopsidedness is the tell. Now we just need a way to measure it. Picture the wound-up curve as a physical wire and find its center of mass, its balance point. When the winding is off frequency, the curve is spread evenly around the origin, so the balance point sits right at the center, basically zero. But when the winding matches the signal, all those peaks pile up on one side and the balance point gets yanked away from the origin. So here is our detector. A center of mass far from zero means this frequency is in the signal. Near zero means it isn't. One number, and it tells you everything. So do it for every frequency. Slowly sweep the winding dial from zero on up, and at each speed record how far the center of mass drifts. Plot that. For most frequencies, the drift is basically nothing, a flat line hugging zero. But as the dial creeps toward the signal's true frequency, the curve balances harder to one side, the drift shoots up, and you get a spike. Sail past it and the drift falls back down. That spike is the fingerprint. We have turned a wiggle in time into a clean peak in frequency. If you want the machinery under the hood, the horizontal position of that center of mass is just the average of the signal times a cosine that spins at the winding frequency. Where the signal is big and the cosine is positive at the same moments, they reinforce and the average grows. Where they disagree, they cancel. This average is what the mathematician Grant Sanderson calls the almost Fourier transform. It is 90% of the real thing, and it already does the whole job. Now the payoff and the reason we opened with a chord. This whole process is linear. That is a fancy word for an almost unfair fact. The transform of two signals added together is simply the two transforms added together. So feed in a 2 Hz tone plus a 3 Hz tone, that tangled green mess from the start, and the frequency plot lights up with two clean spikes, one at 2 and one at 3. The notes fall right out. We unmix the sound. That is the Fourier transform earning its name. Time to make winding around a circle precise, because it is not just a picture, it is exact mathematics. The plane we have been winding on is the complex plane. Rightward is the real direction, upward is imaginary. And a point on that plane is not two separate numbers. It is one complex number, carrying a distance and a direction at the same time. That packaging is exactly what we need to describe spinning. And spinning has a magic key, Euler's formula. E to the ix equals cosine x plus I sine x. Do not let the symbols scare you, read what it says. Plug in a growing number x, and this single expression walks a point around the unit circle forever. It is the most compact way in all of mathematics to say rotate. One little e, and you have circular motion in a bottle. To wind at a chosen speed, we just dial the exponent. E to the 2 pi ift spins the point around the circle exactly f times every second f, our winding frequency, sitting right there in the formula. The real Fourier transform uses a minus sign, e to the minus 2 pi ift, which simply winds the other way, clockwise. Same idea, opposite spin, and that sign is what lets the transform remember not just how much of a frequency is present, but where in its cycle it begins. Now assemble the machine. Take the signal g of t and multiply it by that winding term, that is the signal, wound onto the circle. To find the center of mass, average all the wound points, add them up, divide by how many there are. That sum is the transform in discrete form, perfect for a computer chewing on a finite list of samples. Let the number of samples grow without bound. Let the gaps shrink to nothing, and the sum melts into an integral. That is the continuous version, the center of mass, exact. By convention, mathematicians drop the averaging factor and let the integral run over all of time. What is left is the Fourier transform in its bare, iconic form. G hat of f equals the integral of g of t times e to the minus 2 pi ift dt. Feed it a function of time, it hands you back a function of frequency. Its size at each frequency tells you how strongly that frequency is present. Its angle tells you the phase, where in its cycle that component begins. Two pieces of information, folded into one complex number for every frequency at once. And here is the part that lifts this from a clever trick to a deep truth. It runs both ways. There is an inverse Fourier transform, same formula. Flip the sign in the exponent. That takes the frequency picture and rebuilds the original signal perfectly from scratch. Nothing is lost in translation. The wiggle in time and the spikes in frequency are not two different things. They are the same object seen from two sides. Time and frequency are a matched pair, and you can step freely between them whenever it suits you. Once you can move between time and frequency, a huge slice of modern technology falls out almost for free. A 60 Hz electrical hum in a recording. Transform, find the spike, erase it. Transform back, clean audio, mathematically exact. Every MRI scan you have ever seen is literally an inverse Fourier transform. The scanner measures frequencies, and the image is what those frequencies reconstruct. JPEG shrinks your photos by discarding the frequencies your eye barely notices. And Wi-Fi, 5G, and Bluetooth carve the airwaves into frequency lanes so 1,000 signals can share the same space without colliding. Same idea everywhere you look. But there is a catch that nearly buried this whole idea. Computing a transform the direct way costs about n² operations for 1 million samples. That is 1 trillion. Far too slow to be useful. Then in 1965, Cooley and Tukey published the fast Fourier transform, a way to reorganize the very same computation so it costs only n times log n for that million samples. You drop from 1 trillion operations to about 20 million thousands of times faster. It has been called one of the most important algorithms ever written, and it is the reason the Fourier transform lives inside your phone and every song you stream, instead of only inside a textbook. Here is where the story turns genuinely modern. In just the last few years, the Fourier transform has walked straight into artificial intelligence. Ordinary neural networks look at data one small patch at a time, fine for cat photos, clumsy for physics, where everything influences everything. So researchers built a new kind of layer that does its thinking in frequency space. It transforms the data with an FFT, learns a filter on the frequencies themselves, then transforms back. It is called a Fourier Neural Operator, and because frequencies do not care about grid size, the same trained network works at any resolution, something ordinary networks simply cannot do. It has quickly become the go-to tool for teaching AI to predict how physical systems behave. The showcase is the weather. NVIDIA's FourCastNet uses these Fourier operators to forecast the entire planet's weather, and it runs orders of magnitude faster than the physics-based supercomputer models, turning forecasts that once took hours into seconds. That speed is a superpower. Instead of one prediction, you can run thousands and actually measure the odds of a rare, dangerous storm. Newer versions grew even smarter. They swapped the flat transform for a spherical one, so the math respects the fact that Earth is a ball, not a sheet. The latest generation landed in 2025, a 200-year-old idea about heat, now steering our best guess at tomorrow's sky. And it does not stop at weather. The same frequency space trick is being bolted into the transformer models behind today's AI to mix information faster, and into the image generators that dream up pictures from pure noise. It is not magic, though. These frequency methods have a known blind spot. They capture the big, smooth, low-frequency shapes easily, but they struggle with the finest high-frequency detail, a quirk researchers call spectral bias. Still, the pattern is unmistakable. Reach for a hard problem in modern computing, and more often the Fourier transform is already there, waiting. And then there is the edge of the map. Quantum computers have their own version, the Quantum Fourier Transform, and it is the beating heart of the most famous quantum algorithm ever devised, Shor's algorithm. Here is the astonishing part. The security of almost all online encryption rests on one assumption, that factoring enormous numbers into primes is effectively impossible. Shor's algorithm quietly rewrites factoring as a hunt for a hidden repeating pattern. A period and finding periods is exactly what a Fourier transform does. Running on quantum hardware, it uses interference to make every wrong answer cancel and the right one ring out. A number that would take an ordinary computer longer than the lifetime of the universe to crack could fall in hours. The Fourier transform, in a strange new form, may one day break the locks on the entire internet, which is precisely why the world is already racing to build encryption that can survive it. So step back and look at what we found. We began with a hopeless-looking wiggle and a question that felt impossible, and we cracked it by doing something absurd, winding a graph around a circle and watching where it balanced. Out of that came a single formula that quietly runs the modern world, cleaning your music, imaging your brain, forecasting the weather, and now teaching machines to think and quantum computers to factor. But the deepest lesson is not any one application. It is this: time and frequency were never opposites. They are two languages for the same reality, and the Fourier transform is the dictionary. Wind the signal, average the position, repeat for every frequency. That is the whole idea, and it is as powerful as it is beautiful.